Here are a few examples that look at simplifying expressions that use identities or perhaps trig function relationships that we've been studying. So I want you to keep in mind as we move through these that we talked about the tangent ratio was the same as sine over cosine. We also learned that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So those are the relationships that we've been talking about, and then the identity that we've been talking about is cosine of the angle squared plus the sine squared of the angle equals 1. And you can rewrite those in terms of cosine, where cosine is sine squared minus 1, or sine squared, or not minus 1, it's 1 minus, sorry. Cosine squared is 1 minus sine squared, or sine squared is 1 minus cosine squared. So you can rewrite those in terms of one or the other by just subtracting over the other term. So in simplifying some of these expressions, we'll start with tangent times cosine. So we can rewrite tangent as the sine of x over the cosine of x. And when we multiply that by cosine of x, the cosines end up dividing to 1. And what you're left with is the sine of x. And that's your final simplified answer. For the next one, you have cosine squared of 2 theta plus sine squared of 2 theta. And because 2 theta is the same angle, and you're doing cosine squared of the angle plus sine squared of the angle, we'll actually use the identity that said if you add the square and of the sine and the cosine together, that you get that that's exactly 1. So that's the answer for that one, it's just 1. For this next one, we have secant times cosine. Secant is the reciprocal of cosine. So when we multiply the reciprocal of cosine, 1 over cosine, times cosine, the cosines divide to 1, and we're left with just the value of 1. So regardless of the angle t, if you multiply the secant times the cosine, you will always get the value of 1. Okay. Sine of theta divided by tangent of theta. You can rewrite tangent as sine of theta over cosine of theta. So that ratio is in the denominator. And then you can rewrite that and take that denominator, and instead of dividing it, you can multiply and then do the reciprocal, cosine over sine. The sines end up dividing to 1, and you're left with cosine of theta for your final answer. Right. Next question is going to use the identity that said cosine squared plus sine squared equaled 1. And all it did was subtract over the sine squared term. So we can replace the numerator with just a cosine squared of t. So there's, cosine squared of t is the same as the cosine of t, and then that quantity gets squared. That's the same, but just a different visual representation. So when we divide that by a single cosine of t, you end up canceling a cosine from the numerator and denominator, and you're left with cosine of t in the numerator. All right, the next one has, they're all sine functions, so there's no reason to really rewrite them for this one. But we can take and distribute this -2 through and then play a little bit of cleanup with algebra. So we have 3 sine of t, -2 times 1 is -2, and -2 times -2 sine t is +4 sine t. You have common terms with the 3 sine t and 4 sine t. It's just like adding x's. So if you have 3 plus 4 of them, that gives you 7 times the sine of t, and then you just subtract 2. And there's nothing else you can do to simplify that equation or that expression. All right. The next one involves a quantity that gets squared. So anytime you have a quantity that gets squared, you need to write it out that many times and multiply it. So sine of x minus cosine of x times sine of x minus cosine of x, and then we'll add the 2 sine x cosine of x on the end. For these two quantities that got multiplied out, the two sets of parentheses, we're actually going to FOIL those so that our distribution happens correctly. So we'll do sine of x times sine of x, which is sine squared, Then we'll do sine of x times negative cosine. So that's negative sine x times cosine of x. And then the inner pieces, we'll do negative cosine of x times sine of x. And then our last pieces we'll do plus cosine squared of x. And then we'll just make sure we keep our plus 2 sine of x, cosine of x on the end. Okay, like term-wise, these two terms here, the negative sine x cosine x and negative cosine sine, those are the same terms, even though the pieces, the multiplication is different. Multiplication is commutative, so you're allowed to switch those. And those actually combine to be negative 2 sine x cosine x's if you switch the order on the multiplication there. So you have sine squared of x minus 2x cosine x plus cosine squared of x plus 2 sine of x cosine x. Again, we have some like terms. The sine x cosine x, there's a negative 2 and a positive 2, so those are going to add to 0. So we have sine of x, sine squared of x plus cosine squared of x, and that is the Pythagorean identity, to which you can write that it equals 1. So all that work to get 1 for your final answer. All right. Next one here uses an angle of 2a. So we have the sine of 2a divided by tangent of 2a. And so since I have this tangent function in here, I'm just going to go ahead and rewrite tangent as sine of 2a over cosine of 2a. And that's in the denominator. So if I rewrite the numerator and multiply and do the reciprocal of the denominator, I get cosine of 2a over sine of 2a, and then I'll add 2 cosine of 2a. My sine of 2a is divided to 1. I'm left with cosine of 2a plus 2 cosine of 2a, and those are actually like terms. I have 1 cosine of 2a, and then I add 2 more cosine of 2a, so that makes me have 3 cosine of 2a quantities. Final answer. All right. Last example here. So the cosine squared, it's just the cosine function. It's not the reciprocal of anything. And then on the denominator, it's 1 plus the sine of a. So there's no like identity there. But you can use the fact that cosine squared plus sine squared equals 1. And that if you rewrote that in terms of cosine squared, you'd get that it equals 1 minus sine squared. So you could replace cosine squared with 1 minus sine squared in the numerator. Okay, so next step, you cannot cancel the 1 and a sine. You're not allowed to do that here because there's subtraction and addition in both the numerator and denominator. So the way that works is if you can get factored pieces and the entire quantity is the same, those can be canceled. So when we did squared differences before, it was called a difference of squares, and we did it with polynomials. So if we had like x squared minus 4, we could factor that into x plus 2, x minus 2. Or if we had 1 minus x squared, we could factor that into 1 minus x, 1 plus x, because it was a difference of two things that were squared. So this 1 minus sine squared, we can actually write as a difference of squares. So if I do that, it's 1 minus the sine of a and 1 plus the sine of a, all over 1 plus the sine of a. And now we have a common quantity in the numerator and denominator. Those quantities can divide to 1, and what you're left with is 1 minus the sine of a. And that's your final answer. So you have to factor those into a difference of squares, going back for what we did with polynomials, and then you're able to cancel the entire quantity to get your simplified answer.